Good morning all students. Today we are going to start the new chapter, that is transition and inner transition elements. So this is again the biggest chapter of inorganic chemistry, which is having the weightage 8 marks. See, all the inorganic chemistry chapters having the higher weightage, that is coordination chemistry, it is also having the 7 marks weightage. Then already we completed the chapter P block elements. Its name is now changed. It is group number 16, 17 and 18. It is also having the 8 marks weightage. And this is the third chapter, transition and inner transition elements, which is also called as a D and F block elements. It is also having the weightage 8 marks. So we will discuss what is the transition elements first, that is the D block elements, and after that we will discuss what is meant by inner transition elements. So before starting this chapter, we are already familiar with what is meant by S block elements, what is meant by P block elements. I will explain what is meant by S block elements and P block elements first, and then I am coming to this D and F block. You know, when the last electron enters in S orbital, it is called as S block elements, which contributes group number 1 and group number 2 of the periodic table. Already we learned about the S block elements and the P block elements in 11th standard also. And what about the P block elements? In P block elements, the last electron enters in P orbital. That's why it is called as P block elements. Group number 13 to group number 18, these contributes to the P block elements. Because the capacity of P orbital is 6 electrons, so there are 6 groups in the periodic table, as the capacity of S orbital is only 2. So there are 2 groups in the periodic table, that is a group 1 and group number 2. Now I'm coming to this transition elements. These are also called as the D block elements, remember. So what is this transition elements? As the definition, according to the definition of S block, P block, also in case of D block elements, we can see the last electron enters in D orbital. But this D orbital is not in last shell, it is in penultimate shell. I will explain this penultimate shell. Penultimate is not ultimate shell. Before the ultimate shell, one shell is there. This shell is called as penultimate shell, remember. It is n minus 1, where n indicates the principal quantum number, that is the last shell. So I have given here one example, scandium. Scandium, it is the first element of D block, which is having atomic number 21. If you write the electronic configuration of this scandium, 1s2, 2s2, then 2p6, then 3s2, then 3p6, 4s2, and 3d1. You can see here the differentiating electron enters in the 3d orbital. Here, last shell is 4s. Last shell is 4s, and before this, inside this last shell, there is a penultimate shell. Penultimate, already I explained, this is not last, but it is inside the ultimate shell. That's why it is called as penultimate shell. N minus 1 here, n indicates 4. That is the principal quantum number. 4 minus 1, it is 3. So electron enters in 3d orbital. So according to the definition, the last electron enters in a d orbital, or d orbital is partially filled or progressively filled. These elements are called as D block elements. So this is a difference between S block elements, P block elements, and in case of D block elements, the last electron enters in D orbital, which is in penultimate shell, which is not present in last shell, remember. So these are also called as the transition elements, and why this transition word is used, I will explain. Because these are placed in the periodic table. I will show the periodic table to you. See this periodic table. So in this periodic table, extremely right hand side, we can see here p block elements are there, group number 13 to group number 18. All these are the p block elements. Extremely left hand side, there are S block, and in between this S and P block, there are D block elements are there. We can see this is a D block, starts from group number 3 to the group number 12. These are in transition. So S block, in between S block elements and P block elements, these D block elements are kept. That's why these are also called as transition elements. Again, I am coming to this plus side. So according to the IUPAC, the new definition is made. Transition metals are the metals. These are defined as which is having incomplete D subshell, or D subshell is partially filled, not completely filled. So in all these elements, group number 3 to group number 12, the d orbital is half filled, d orbital is incompletely filled or partially filled. These are the exceptions. These are the exceptions. Zinc, which is having completely filled d orbital, cadmium, which is having completely filled d orbital, mercury, which is also having completely filled d orbital, and this is a copernicum, which is also having the completely filled orbital. So these elements are actually not included in, according to the definition IUPAC nomenclature system. These zinc, cadmium, mercury, and copernicum, these are not included in transition elements or D block elements, but as these elements are the last elements, this is a 3D series, because the electron enters in 3D. This is a 4D series, this is a 5D series, and this is a 6D series. So as these elements are the last elements of 3D, it is 4D series, this is 5D series, and this is 6D series. So its chemistry is studied in transition elements, but these are the not members of transition elements, remember. Zinc, cadmium, mercury, and copernicum. So 3D series, just I explained. In case of transition elements, there are 4 series. First series is 3D series, which starts from scandium to zinc. See, this is a 3D series, which starts from scandium, atomic number is 21, and ends to atomic number 30, that is zinc. This is 3D series because electron enters in 3D series. Next series is 4D series because electron enters in this 4D. From yttrium, atomic number is 39, to the cadmium, atomic number 48. I will show this yttrium. See, yttrium is atomic number 39 and it ends with atomic number 48. Last element is cadmium. Then this is 3D is completed, 4D is completed. This is 5D series. This is very important. This is starts from lanthanum and ends with mercury. But from this lanthanum, there are these elements are not included. See, from 58 to 71 means only lanthanum is included, but after lanthanum there is a series of 14 elements. This is the cerium to lutetium. These elements are not included because these are included in F block elements. So except cerium to the lutetium, atomic number 57 to atomic number 80. These elements are, this is 3D, this is 4D, this is 5D elements, 5D series. But remember, except this cerium to lutetium, because cerium to lutetium, it is a lanthanide series. And similarly, from this actinides to the copernicum, from 89 to 1112, except these thorium to the lawrencium. So again, these 2 series are not included in transition elements because in this electron enters in F orbital. In all the lanthanides, electron enters in 4f orbital, and in case of actinides, electron enters in 5f orbital. So these two series, that is atomic number 58 to 71 and atomic number 90 to 103, these contributes to the block elements. Remember, these two series. Actually, these are included in group number 3, period number 6, and period number 7. Period number 7 is actinide series. Period number 6 is lanthanide series. These are, for the convenient purpose, these are placed below the periodic table, but actually these are included in this period number 6 and period number 7. All these lanthanides and actinides are included in group number 3, remember. So all these 4 series are completed. Already I explained this is 5D series, lanthanum to the mercury, except the cerium to the lutetium, because these are lanthanides, and 6D series, that is from actinium to copernicum. These are the newly discovered elements, atomic number 112, 113, 114, 115, 116, 117, and 118. So these are the new elements discovered. From this thorium to lawrencium, these are not included in the transition elements because these are the parts of actinides. So this is the general introduction is completed. So with the help of this periodic table, we can clearly identify where the D block elements are kept. D block elements are kept in between S block and P block, from group number 3 to group number 12. First series is period number 4. It is scandium to zinc, 3D, yttrium to cadmium. This is a 4D series from lanthanum to mercury. This is 5D series, and from actinides to copernicum, this is 6D series. So this is a entire D block is there. See, we have to study the properties of the series number 1, only 3D series, that is scandium to zinc. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. I will also give one hint how to remember these first series. This first series is only for our study. These elements are not for our study. Yttrium to cadmium, lanthanum to mercury, actinium to copernicum. So only we are interested in this 3D series. So position, just I explain you the position of this periodic table, where because for the board examination, the question will be asked, write the position of the transition elements in the periodic table. For 1 mark, the question will be asked. So we have to write the position. These transition elements are kept in between S block elements and P block elements, and from group number 3 to group number 12. And also mention the periods: 4 period, 5th period, 6th period, and 7th period. So the position and these series are also specially shown to you. Scandium to zinc, this is 3D series. Then yttrium to cadmium, this is 4D series. Lanthanum to mercury, except these elements are not shown. Lanthanides are not shown here. That is 58. 58 to say 58 to 71, these elements are not shown here in this series also. See, direct 57 to direct 72 is given. So these lanthanides are not included, and also actinides are not included. We can see here 90 to 103. These 14 elements also not shown in this actinide series. So this 3D series starts from scandium and ends with zinc. Then I'm coming to the electronic configuration of the D block elements. So this is general electronic configuration is N minus 1D, where N indicates the principal quantum number. N minus 1D means here N is the principal quantum number, and generally this is a 1 to 10. 1 to 10 means this D orbital is progressively filled. First scandium, in case of this scandium, first it will be 3D1, then it will be 3D2, 3D3, 3D4, then it will be 3d5, then it will be 3d6, 3d7, 3d8, 3d9, and 3d10. So this d orbital is progressively filled. But this, this chromium and this copper shows exceptional behavior. I am coming to that point also. So if the general electronic configuration is asked for the board examination, we have to write the general electronic configuration is n minus 1d, where n can be 4, n can be 5, n can be 6, and n can be 7. So according to this series, if this is 3, in this case, the value of n is 4. In this case, value of n is 5. In this case, the value of n is 6. And in this series, the value of n is 7. N minus 1, that is 4 minus 1, it is 3D series. In case of this 4D, the value of n is 5. In this 5D series, the value of n is 6. That is 6 minus 1 is 5D. And in this series, 6D at as 6D is there, so value of n will be 7, means it will be 7s2. But we are only interested in this 3D series. So I am coming to the electronic configuration of 3D series. We can see clearly argon. This is written with respect to inert gases. So argon means the atomic number of argon is 18. So 3D 1 to 10, 4s 1 to 2. This 4s 1 to 2, it is shown because of the copper and chromium. Only copper and chromium having only one electron in the s orbital. Then in 4D series, krypton, this is with respect to inert gases. So it is 3D, 4D, 5D, 6D. We can see 1 to 10 means d orbital is progressively filled. First one electron, same for see here. It will be 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, 3D10. Like this, it will be 4D1, 4D2, it will be 5D1, 5D2, like this. So this electronic configuration, general electronic configuration is shown. With this general electronic configuration, clearly we can identify this d orbital is progressively filled from 1 to 10. And this s orbital having electrons 1 to 2, because the capacity of s orbital is only 2. But see here, in case of 4D series, it is shown 5s0 to 2, because no single electron is there in case of s orbital. Also, I am showing this series here. Yes, we can see, this is the outermost electronic configuration of first series. This is 3D series, this is 4D series, this is 5D series, and this is 6D series. So in case of this 4D series, we can see here, in case of s orbital, 0 electrons are there. See, in case of palladium, the 0 electrons are there. That's why the general electronic configuration is 0 to 2. But in case of this 3D series, we cannot see 0 electrons in the 4s. See, 4s. There is no any 0 electron is there, but only in case of chromium and copper, we can see 1 electron is there. That's why the general electronic configuration is 1 to 2, because only 1 electron or 2 electrons are there in 4s. So it is written 1 to 2, but in case of 4D series, it is written 0 to 2, because 0 electrons are also there. Then in case of 3D is completed, 4D is completed, this is 5D series. See, in case of this 5D series, we can write the electronic configuration 1 to 2, because in case of platinum, in case of AU, that is Orium, it is gold. Only 1 electron is there. Then in case of 3D, 4D, 5D, 6D series also, we can see here general electronic configuration is 1 to 2. So the general electronic configurations are shown here. This is 1 to 2 also. This is also 1 to 2. This is also 1 to 2. Directly 2 is written. Here 0 to 2 is written. Why I am giving more stress to this general electronic configuration? Because it is asked for 1 mark. Write the general electronic configuration of 3D series, 4D series, 5D series, 6D series, they will ask. As I explained earlier, these are the zinc, cadmium, Hg, and coppernicum. These are in these elements. In case of zinc, d orbital is completely filled because there are 10 electrons. I will show the electronic configuration of the 3D series. See, in case of scandium, atomic number is 21. See, the electronic configuration is a 3D1 for S2. This is 3D2. This is the D is progressively filled. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, in case of zinc here, the d orbital having the 10 electrons, it is completely filled. But according to the definition of IUPAC, if the d orbital is completely filled, it is not included in transition elements or d block elements. So according to the definition, this zinc is not included in case of d block elements or transition elements because its d orbital is completed. See, we can see clearly here 10 electrons are there. So it is not the member of the transition series. Then similarly, this cadmium, mercury, and coppernicum also, these are the not the member of these transition elements, but for the study purpose only, these are included in transition elements. Remember, as these are the last members of 3D series, because zinc is the last member of 3D series, this cadmium is the last member of 4D series, this mercury is the last member of 5D series, and this coppernicum is the last member of 6D series. See here, zinc is the last member, then cadmium, and then mercury, and this coppernicum, because the d orbital is completely paired. 10 electrons are there, also the 10 electrons are there here. In case of mercury also 10 electrons are there, and in case of coppernicum also the 10 electrons are there, but only the series will be changed. This is a 3D series, this is a 4D series, this is 5D series, and this is 6D series. Only this is the difference. Copper is included in this transition elements because we can see here, I am coming to the anomalous behavior of chromium and copper. See, like zinc also, see, zinc d orbital is completely filled. 3D 10 electrons are there. That's why it is not included in transition elements. But any student can ask me, sir, also this copper also, the d orbital is completely filled. So why it is included in this transition elements or d block elements? I will explain the reason. According to the IUPAC, the definition was when the d orbital is completely filled. See, I will show the definition again. What is the definition of IUPAC? The metals which having incomplete d subshell either in neutral atom or in their ions. If we see the ions of copper, if you see the ions of copper in case of first to oxidation state, plus 2 oxidation state, sorry, plus 2 oxidation state means these two, if these 2 electrons are given, see, if these 2 electrons are given from this is a expected electronic configuration and this is observed electronic configuration. If the plus 2 oxidation state of copper means if this 1 electron is removed and we have to remove 1 electron from this 3D. So in case of 3D, there will be the 9 electrons. So if the 9 electrons are there, it can be the member of the transition elements. But if D having 10 electrons, it will be the not member of transition series, remember. So for the examination, this question can be asked, why the copper is included in transition elements or in case of d block elements, though its d orbital is completely filled. So your answer should be like this: copper can show plus 2 oxidation state. So in case of plus 2 oxidation state, the d orbital containing 9 electrons, so d orbital is not completely filled, and according to the definition of IUPAC, copper can be the member of d block elements. Remember, this is a very, very important question. So how to remember this 3D series scandium to zinc? I have prepared one short form for you. The first one is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. This is 3D1, 3D2, 3D3, 3D4. But this chromium and this copper shows exceptional behavior. First, I will explain. This is scandium is 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, and 3D10. So 3D10 is completed in zinc. Now, how to remember this transition series? Sachin Tendulkar, very crazy man, because for remembering this scandium, I have prepared this short form. Sachin Tendulkar, T for Tendulkar, V for very crazy man, gives free coaching to Nitin's cousin. So I have prepared for remembering the transition series. Also, in case of Marathi, we can remember like this: Kati Vakramana Pekoni Kuzana, because this Kati means scandium, titanium. Vakra means this is vanadium and chromium. Mana, it is for manganese. Fe, it is for iron. Cobalt. Ni, nickel. Ku, it is copper, and Zan, it is for zinc. So either we can remember this one, either we can remember this one, because without knowing the sequence of these elements, we can't remember the electronic configuration, because electronic configuration can be asked for the examination also. They will not give the atomic number. Remember, this is scandium is 21, this is zinc 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. This is 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, 3D10. But only this chromium and copper shows exceptional behavior for getting the extra stability. We can see expected electronic configuration is like this, but observed electronic configuration is changed only in case of chromium. See, in case of chromium, this is having 3D5, and in case of copper, it is 3D10. Why this is happening? In 11th standard also I explained this copper and chromium, for getting the extra stability, one electron from this 4s is shifted in 3D. So 3D becomes 3D5. 3D5, it is half filled, because the capacity of d orbital is 10 electrons and 5 electrons. These are half filled. So chromium becomes extra stability, acquires extra stability. And when it is completely filled, it also acquires the extra stability. So for getting the extra stability, one electron from 4s. So 4s is having only one electron here in case of chromium, and in case of copper. So this is exceptional behavior of chromium and copper. Remember, this also can be asked for the examination for 2 marks. Exceptional behavior of chromium and copper. Then, so this electronic configuration part of this 3D series is completed. We can remember scandium is 3D1, zinc is 3D10. It will be titanium will be 3D2, vanadium will be 3D3, chromium exceptional behavior. It is actually expected. It is a 3D4, but observed electronic configuration, it is a 3D5 for getting extra stability. So extra stability, forget about the extra stability. For understanding purpose, scandium is 3D1, it is 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, and 3D10. So this d orbital is progressively filled according to the definition of transition elements. This d orbital from scandium to zinc is progressively filled, and in case of zinc, it is completely filled. So if it is completely filled, it is not included. So zinc is not included in this transition, but for studying the chemistry only, it is included in this transition elements. But actually, it is not transition element, remember. Then, just I explained this electronic configuration of chromium and copper. We can read at your home for getting extra stability. This is also explained. Then I am coming to the oxidation state of first transition series. So oxidation states means what? If for the combination purpose, these transition elements can donate the electrons. So all these transition elements shows the positive oxidation state. We can see the table is given below. This table is given below because before this table, you must know the electronic configuration, outer electronic configuration of 3D series only. Because we are discussing with this 3D series only, that is from scandium to zinc. Scandium, now the electronic configuration is 3D1, 4s2, titanium 3D2, then vanadium 3D3, chromium 4, manganese 5, iron 6, cobalt 7, nickel 8, copper 9, and zinc 10. Now we are familiar with the electronic configuration. But I want to explain one thing here. This energies of this 3D and 4s, these are very closer. Almost it is same. Almost it is same. So we can transfer the electron from this 4s to 3D1 also. So for the combination purpose, for the binding chemical bonding purpose, these electrons can be what you can say. In excited state, one electron can be shifted. So in case of 3D series, if you compare the oxidation state here, only this chromium can show, only this copper can show +1 oxidation state, but it is very unstable because there is only one electron in case of s orbital. Chromium also shows the +1 oxidation state, but it is a very unstable. It is not shown here. Only this chromium and copper shows +1 oxidation state, but it is very unstable. So for the chromium and copper, as there is only one electron in s orbital, we can see here for s1. So copper can show +1, but it is a very unstable. That's why it is neglected. In case of chromium can also show +1 oxidation state, but it is a very unstable. It is neglected. So in case of oxidation states of first transition series, the lowest oxidation state is +1, and we can see the highest oxidation state is +7. These oxidation states shown with bold types, these are the very stable oxidation state. So oxidation state I will explain. For the oxidation state, you must know the outer electronic configuration. We will discuss about the scandium first. So in case of scandium, see the outermost electronic configuration is 3D1 4s2. So scandium can give these 2 electrons. If these 2 electrons are given, the oxidation state will be +2. If the 3 electrons are given, means 4s2 and 3d1, it will show +3 oxidation state. In case of +3 oxidation state, this 3d becomes 0. 3d 0, it is a stable oxidation state of scandium. Then I am coming to the titanium. See the outermost electronic configuration of titanium is 3d2 4s2. If these 2 electrons are given, the oxidation state will be +2. Then 3 electrons are given, means these 2 and 1 electron from this 3d. So it will be +3. And when it will be stable, when these 2 electrons and when also these 2 + 2, 4 electrons are given, means 4s2 and 3d2. All the 4 electrons, when these are given, it shows the stable oxidation state. Means if this 3d will be 0, it is +3 stable. In case of titanium, if the 3d is 0, it will be +4, it will be stable. Then I am coming to vanadium. Same for vanadium, when these 2 electrons given, it is +2. When 3 electrons is given, 3d1. In case of 4, it will be 3d. When 4 electrons are given, the 3d will contain 1 electron, and when all the 5 electrons will be given, these 3 and these 2 electrons are given, 3d will be 0. So +5 is the stable oxidation state in case of vanadium. Because last year, in case of 2019 board exam, the question is asked for the MCQs. which is a stable oxidation state of scandium. For 1 mark, the question is asked. So the answer was +3 oxidation state. It is the stable oxidation state of scandium. Because when it will be stable, because 3D, when 3D it is 0, when 3D will be 0, 2 plus 3 electrons will be given. When it titanium 3D will be 0, 2 plus 2, 4 electrons will be given. In case of vanadium, when the 3D will be 0, because when the 5 electrons will be given, it will be 0. Now I'm coming to the chromium. When the chromium will be, in case of chromium, when the 3D will be 0, when the 6 electrons will be given. So we can see here, +6 oxidation state is also stable, and +3 oxidation is also stable. +3, when it will be +3, when this 1 electron will be given, and when this 1, and when 2 electrons will be given. So 3D will contain, see, when 1 electron will be given, it will be +1, but chromium shows very less compound, very unstable. +1 oxidation state is very unstable. So that's why it is not written here. +2, when it shows +2 means this 1 electron from 4s and 1 electron from 3D. So 3D will contain the 4 electrons. In case of +3, this 1 electron and these 2 electrons will be given. So the 3 electrons will be there in case of 3D. So +3 oxidation state and +6 oxidation state is more stable oxidation state in case of chromium. But this manganese shows the variable oxidation state, +2, +3, +4, +5, +6, +7. This is very interesting. Why the manganese shows +2 oxidation state is more stable. I am coming to why this is more stable. Because if these 2 electrons are given from this 4s, 3D contains the 5 electrons. It is exactly half filled. Because the capacity of the d orbital is 10 electrons. When it is half filled means when d contains 5 electrons, it will be more stable. It will be more stable, but this statement cannot be we apply here in case of chromium, remember. So manganese, when it becomes 3D becomes half filled means the capacity of the d orbital is 10 electrons. When it contains 5 electrons, it will be stable. So this question is asked for board exam in case of March 2013. This question is asked. Again, chemistry lecture is there at 10:10. So remaining part of this chapter we will complete in the next lecture, 10:10. So I am going to stop here. Again, we have to join for the lecture at 10:10.